Hello, my name is Dulce Ordaz and I'm going to present my app from the Yellowstone problem or case study. First, the purpose of the app is to predict the development of the population. It means the growth and decline of elks, coyotes, and wolves in the Yellowstone Park, as they have introduced wolves in 95 and 96, and the park want to predict how the population of this species will grow or decline in 200 years or the years that the user desire. Here I have my design view of my application, and I desire to put the differential equations with each coefficient that I obtained in my previous code of the point 3 of point 4 of the case study report. And in this way, the user will be able to see the how the different species interact. For instance, here we have that the coyotes and growth or population declines, as well as the wolf. Then I'm gonna start to run my application. Wait, trunk. And then I'm gonna yeah. Well, here's my application after pushing the run button, and then here the user will be able to put the years that he or she decide. For instance, that year for the case of the report, the user asks 200 years, and then I only have to push the data button. It's the only thing that the user has to do. And I don't know why that figure one appears, but here are my plots. And here in the first row, we have the elk data, the second row, the coyote data, and in the third row, the wolf data. And in the first column of graphs or plots, we have the data as the Yellowstone Park provided. And in here, we didn't change, well, I didn't change anything. All the data is as it is. And then well, this plot serves to see how the data changes over time and how the data is before applying the simulation or the model to the population. Well, for to predict the population. Then in these columns, we have the numerical versus analytical comparison. And for example, in the data with numerical, we have the difference between row 1 and row 2 of coyotes or elks or wolves. And this repeated 10 times because we have 11 rows of data. So here we have 10 different points, 3, 6, 9, and 10. And for the analytical solution, that is this black line, it was created using the linear algebra that we developed during classes. And for instance, the first matrix is the one of delta x1, delta x2, and this n times, that it's n equal to 10, equals to the matrix of x, xy, and all the variables. And also, this matrix is of 10 rows times the matrix of coefficient 1, a2, a3, in this case, then B1, B2, and C1 and C2. And then we obtain the A matrix, the vector of A. So each one was extracted, A1, A2, and A3, B1 and B2, and C1 and C2. And then these values were put in this part. So these equations were modeled and we obtained these black lines. And then for the long-term dynamics, these long-term dynamics were modeled using the OD45 solver of MATLAB. So because this type of differential equations cannot be solved using normal integration, so it was required a mathematical solver. And these plots show us how the population changes over time or fluctuates. For instance, in the elk graph, we can see how the elks grow and decreases and then grow and then decreases, following a type of oscillation. And then for coyotes, we can see that it decreases almost to extinction, and which have sense because the wolves and elks reach a kind of equilibrium, and then for the wolf graph we can see that also they decreases and then grow and they decrease. So it has sense because as elks decreases, also wolves decreases, but kind of a little after because they start to starve or suffer from starvation. And yeah, it's like they fluctuate and they have this equilibrium. And that's all for my application and for my job. And Merry Christmas, Professor. Bye.